In this video, I'd like to talk about the atomic spectrum of hydrogen and about the Bohr model of the hydrogen atom, which explains the atomic spectrum. The emission spectrum of an element is the light that is emitted by excited state atoms of that element when you look at it through a spectroscope or diffraction grating or prism to look at the constituent wavelengths. And you'll recall that if I take white light, pass it through a slit and through a prism, we see that white light is actually made up of all of the colors of the rainbow. That is called a continuous spectrum. It contains Roy G. Biv. However, if you take excited state hydrogen atoms, you may recall, from a discharge tube, pass them through a prism, instead of seeing a line spectrum, instead of seeing a continuous spectrum, you see only certain characteristic colors. That is called a line emission spectrum. Now, what does that tell us about the hydrogen atom and all other atoms for that matter? It tells us that the energy levels are quantized, which means that the hydrogen atom can only exist in certain energy levels, which we characterize by the quantum number n. 1 corresponds to the ground state or lowest energy state, 2 corresponds to the first excited state, and so forth. When the hydrogen atom undergoes a transition from a higher energy state to a lower energy state or vice versa, only a specific amount of energy can be absorbed or emitted. And that amount of energy is reflected by the characteristic wavelength and frequency. So if I consider delta E to be the difference between the final state and the initial state, that will be reflected in the frequency of light that I observe and the wavelength of light that I observe as well. Now, I can represent that by this energy level diagram. Each of the horizontal lines corresponds to one of the quantized energy levels in the hydrogen atom. N equals 1 is the ground state, N equals 2 is the first excited state, and so forth. Each of the vertical arrows going from a higher quantized energy level to a lower quantized energy level represents a transition from the higher energy state to the lower energy state. Okay, and again, remember that the amount of energy contained in the photon of electromagnetic radiation that is emitted when the atom undergoes that transition is equal to the difference between the higher quantized energy state and the lower quantized energy state, and that energy is reflected in the wavelength of light that you see. It turns out that all of the transitions of the hydrogen atom that end up in the N equals 2 quantized state, or the first excited state, we call the Balmer series, after the dead white European male who observed them. These are the ones that happen to be in the visible range, and in fact, the lowest energy from N equals 3 to N equals 2 is the red line that you see in the emission spectrum of hydrogen. Okay? Those that end up in the ground state, the Lyman series, correspond to greater amounts of energy being given off, and therefore shorter wavelength. Those would correspond to transitions in the ultraviolet series, whereas those that end up in the second excited state or N equals 3 state, the Paschen series, correspond to lower amounts of energy being given off, and therefore longer wavelengths. Those are in the infrared. How do we explain quantized energy levels in the hydrogen atom? Well, the first person to come up with both a qualitative and quantitative explanation was Niels Bohr, for which he won, I believe it was the first Nobel Prize in Physics. And I'm going to go through very quickly the qualitative description of the Bohr model of the hydrogen atom, and then we will move shortly to the quantitative version of it. Bohr says, I can explain quantized energy levels by proposing that the electron travels around the nucleus of the hydrogen atom in circular orbits. The energy of the electron, and therefore of the atom, increases with distance from the nucleus. That is, as you go to a larger orbit, that corresponds to the hydrogen atom being in a higher energy state. The electrons can only be in orbits of certain size which have fixed energy levels. That explains why the energy is quantized. If the energy of the atom corresponds to the size of the orbit, and if the size of the orbits are fixed, then the energies are fixed as well. When the electron is in the smallest orbit, the one closest to the nucleus, which corresponds to the lowest energy, the atom is in its ground state. When the atom gains energy, the electron is promoted to a higher energy orbit. When the atom returns to the lower energy state, the electron drops down to a lower energy orbit, and the atom emits energy. And importantly, the energy emitted by the atom, and therefore the wavelength of electromagnetic radiation that is observed, is equal to the energy difference between the initial and final orbits. And each line in the line emission spectrum corresponds not to an energy level, but to a specific transition from one higher quantized energy level to a lower quantized energy level, which corresponds to a lower energy orbit. Now, you've all seen this model before. The green dot in the center corresponds to the nucleus. The dotted circles correspond to the orbits of specified size and therefore of quantized energy. And the dot moving from n equals 3 to n equals 2 corresponds to the electron dropping down from the third excited state to the first excited state and giving off a photon of electromagnetic radiation containing an amount of energy equal to the difference between those quantized states. The wavelength is reflected by that color. Now, the problems with the Bohr model were, first of all, we know from classical physics that the electron cannot be moving in a circular pathway. If it were, it would be continuously giving off electromagnetic radiation, which we don't see. Bohr knew this, but he forged ahead anyway. The other problem was that although folks worked on this for a long, long time, he could only come up with a quantitative model that worked for a one-electron system that is a two-body problem, for example, the hydrogen atom, the helium monocation, the lithium dication, etc. So why do we still teach the Bohr model? Well, even though qualitatively it was incorrect for the hydrogen atom, it was absolutely correct quantitatively. Okay? And he was able to come up with an equation to actually calculate the energies of the quantized energy levels. Okay? And it looks like this. E sub n, meaning the energy of the nth quantized energy level, is equal to negative 2.178 times 10 to the negative 18 joules, a constant that he derived from fundamental physics, times the product of z squared over n squared. Z is the nuclear charge, which for hydrogen is going to be equal to 1, where n is the quantized energy level. We can use this to calculate differences in energy levels and therefore amounts of energy absorbed or emitted in transition by writing this out for n initial and n final, n final and n initial, and subtracting and collecting terms and leaving out the z because we know z is equal to 1 for hydrogen. We obtain this, which is sometimes called the Rydberg equation after the person who used it most frequently. Delta E equals E final minus E initial is equal to this numerical constant, which is sometimes called the Rydberg constant, times 1 over the square of the final quantized energy level minus 1 over the square of the initial quantized energy level. And again, remember, the significance of this is that once we can calculate this energy difference using this equation, we can relate it to the wavelength of electromagnetic radiation. So, if the final energy level is greater than the initial energy level, then that means the atom gains energy, and delta E from the atom's point of view is positive. On the other hand, if the final energy is lower than the initial energy level, then that means that the atom loses energy, and delta E therefore is negative. So let's do some problems in which we apply the Rydberg equation to calculate quantities. Okay? Here's what you should be able to do. Given the initial and final states, that is n final and n initial, calculate the energy corresponding to that transition and therefore the corresponding wavelength or frequency of electromagnetic radiation. Or even more fun, if you are given the wavelength or frequency of the transition and either the initial or final state, calculate the other one. Let's do some problems. Calculate the wavelength of light emitted when the n equals 4 to n equals 3 transition occurs in the hydrogen atom. What type of electromagnetic radiation is this? Well, n initial is equal to 4, n final is equal to 3. So I can simply plug into the Rydberg equation. Delta E equals negative 2.178 times 10 to the negative 18 joules times z squared is just 1 squared. We can leave that out since it's the hydrogen atom. Times 1 over 3 squared minus 1 over 4 squared. And that's equal to a value of 1.059 times 10 to the negative 19 joules. And then to calculate the corresponding wavelength, I'll use wavelength equals hc over delta E. By the way, this is negative because we are going from a higher energy state to a lower energy state, so delta E is negative. But when I calculate the wavelength, I'm going to leave the negative sign out and just take the absolute value because negative wavelength doesn't mean anything. Okay, now, I don't know about you, but I'm getting tired of writing out h and c each time, so I'm simply going to use the product of h and c and come up with my own constant, which has a value of 1.986 times 10 to the negative 25th joule meters. divide that by my 1.059 times 10 to the negative 19 joules. And because nanometers are sometimes more useful to consider than meters, I'm going to multiply this by 10 to the 9th nanometers per meter, and that gives me a wavelength of 1,876 nanometers, which is in the infrared region. I do not expect you to know that, but if I give you a spectrum like you saw earlier in the video, you should be able to pick that out. Okay, let's do one final problem. And to be honest, folks, here, okay. Represent the n equals 4 to n equals 3 transition on an energy level diagram for the hydrogen atom. Hard problem. Let's see if I can get this. Yes, got it. Here's my favorite type of problem. An excited hydrogen atom emits light with a wavelength of 397.2 nanometers to reach the energy level for which n equals 2. In which principal quantum level did the electron begin? Well, let's write down what we have. Wavelength equals 397.2 nanometers. N final equals 2. And initial is what we're trying to find. Sounds like we got some algebra ahead of us. I think a useful thing to do to begin with would be, since we know the wavelength emitted in this transition, we can calculate the energy change. So I will rearrange my equation. I'll simply use delta E equals hc over lambda is 1.986 times 10 to the 25th. Sorry, that's 1.986. 10 to the negative 25th joule meters over my wavelength of 397.2 times 10 to the negative 9th meters. I can simply replace nano with 10 to the negative 9th, and that gives me a value of negative 5.000 times 10 to the negative 19 joules. Now you ask me, Bob, where did that negative sign come from? It came from the fact that we were told that this is the wavelength of light being emitted when the atom goes from a higher quantized energy level to a lower quantized energy level. From the atom's point of view, the system namely, it is losing energy, so we have to make that delta E negative. None of the math will work at this point if you do not make delta E negative. If it were a problem involving an atom gaining energy and going from a lower quantized state to a higher quantized state, we would make the energy positive. So now I'm going to write out the Rydberg equation. Delta E equals, I'm going to write 2.178 times 10 to the negative 18th joules as just R for Rydberg. I'm going to represent that as R, and I'll substitute that in later. 1 over n final squared minus 1 over n initial squared. Negative delta E over R is equal to 1 over n final squared minus 1 over n initial squared. Do some rearranging. 1 over n initial squared equals 1 over n final squared plus delta E over R, which is equal to 1 over 2 squared plus negative 5.00 times 10 to the negative 19th joules. Remember we said delta E is negative, over 2.178 times 10 to the negative 18th joules is equal to 0.25 minus 0.2296 to evaluate that equals 0.02043, and this is 1 over n initial squared. So now I will reciprocate and take the square root, and I get that my initial value of n is 1 over the square root of 0.02043, which on my calculator is 7. So that means in this transition, the hydrogen atom started in the 7th quantized energy level, and in dropping down to the 2nd quantized energy level, it emitted a photon of light with a wavelength of 397.2 nanometers. And that's about it.